See you, Miller.
See you. All right, let's take a look at some of these problems from class the other day where we were working with the fundamental theorem and its connections here. I'm going to work a preferred solution and then an alternative solution. You can see which one you like better, maybe which one's more efficient. So the preferred solution for part A here, which is to find f and then to find the value of c. The preferred solution would be to take the derivative of both sides of this equation so that we can get the f out of the integral. So I'll go ahead and write this out. The derivative of the left side is the derivative of 5x cubed plus 40, and the derivative of the right side is the derivative of the integral function c to x f of t dt. The left side presents no new issue. We could have done this a long time ago. The derivative of this function here is 15x squared, and then the derivative of the constant part is 0. Now the new part here, the fundamental theorem tells us that the derivative of this integral function is the integrand as a function of x, so it's simply going to be f of x. And so that is the big discovery with the fundamental theorem that we need to take forward with us into more challenging problems. So we have f, and now we want to solve for c, and so we're going to go back to that original equation and plug in f since we now know the value of f. So 5x cubed plus 40 is equal to the integral from c to x of f of t dt, and f of x is 15x squared, so f of t will be 15t squared dt. And now I'll use the other part of the fundamental theorem, which tells us how do we evaluate definite integrals. So I'll treat this as a function, take its antiderivative, which will be 5t cubed, and then we're going to plug in our two limits, c and x, and subtract. So I'll have 5x cubed minus 5c cubed, and we'll take a look and see what we can do with the other side about solving for c. There are 5x cubes on either side, so those will cancel out, and we have negative 5c cubed equals 40. Divide both sides by negative 5, we'll get negative 8. Take the cube root of both sides, and we'll get c is equal to negative 2. The alternative approach to finding f would be to actually write out what is the integral of c to x of f of t dt, and we fortunately in this case have a symbol for that. The antiderivative of lowercase f of t dt would be capital F of t, and then we'll plug in our limits c and x and subtract. And here we have to be on our game because we have to understand that capital F of x is a function while capital F of c is a constant, it's a number. And my next step would be to take the derivative of both sides. So once again on the left side I'll get 15x squared. On the right side the derivative of a constant is 0, so this capital F of c is going to disappear, and the derivative of capital F of x is lowercase f of x. Okay, so that's how you might go about finding f a different way than over here, and then you go about finding c the exact same way. Pause. Okay, in this problem here we're presented with a graph. This is the graph of f, and they define a function g to be the integral from 0 to x of f of t dt. So g is the area finder under the graph of f, starting at 0 and ending at any value x we'd like to use. So that's a little note I like to keep track of in the beginning here as I progress forward here. So g is the area finder, among other things. Part A asks you to find g of 3. So g of 3, if I just follow straight from this equation, g of 3 will be the integral from 0 to 3 f of t dt. And in this situation, I will interpret this as the area, the signed area, between the graph of f and the x-axis on the interval 0 to 3. So if I look up the graph, I'm talking about this area from 0 to 2, which is a quarter of a circle. That'll count as positive area. And this triangle from 2 to 3, which will count as a negative area. So if I just go ahead and calculate those, I'll be finished. The radius of this circle is 2, so pi r squared, 4 pi would be the area of the entire circle. We only want a quarter of that, so pi, so we'll take away from here. And this is a triangle. Two sides, base and height, are both 1, so 1/2 base times height gives us a half. This has to be counted as negative because this portion of the graph is below the x-axis. Part B asks you to find all values of x on the open interval -2 to 5, where g, remember g is the area finder, has a relative max. Okay, relative or local max. Justify your answer. To answer this question, we need g's derivative. So g prime of x, if we go back to this equation here, we take the derivative of both sides. The derivative of an integral is the function on the inside, the integrand, as a function of x. So this graph that I was given is the graph of f, which is also the graph of g primed. Relative maxes occur when the derivative of a function changes from positive to negative. I can see this occurs at x equals 2. I do not know the y value where this occurs, so I would say x equals 2, and as my justification, I would say g primed changes from positive to negative. Part C asks you to find the equation of the tangent line to the graph of g at x equals 3. To do this, we need two things. We need the ordered pair at 3, so we need g of 3, and luckily we've already calculated that in part A. So g of 3 equals pi minus 1/2. We also need the slope of g at 3, that's g prime to 3. And in part B, we've already calculated g primed to be f. So g prime to 3 is f of 3. And we can get that from looking at the graph and see that that's a value of -1. From here, we just want to write the equation of a line that has this slope, -1, and goes through the ordered pair 3, pi minus 1/2. So that will be y equals pi minus 1/2. In this case, minus, because the slope is -1, so I'll put -1 times x minus 3. Which can be simplified, but there's no need to in this case. Part D says find the x-coordinate of each point of inflection of the graph of g. On the open interval -2 to 5, justify your answer. Points of inflection by definition are where the first derivative of a function changes from increasing to decreasing. So I'm looking for where g primed changes from increase to decrease or vice versa. In part B, we calculated g prime to be f. So I can look at the graph of f and just determine where does that graph change from increase to decrease or vice versa. I can see that f has a local max at 0 and a local min at 3. And so those will be my two values that are points of inflection for the graph of g. And there's my justification. I just got to fill in the two x values, x equals 0 and x equals 3. Since g prime changes from increasing to decreasing or vice versa at these values. This is a similar problem. The graph is not a nice geometric region that you can find areas for, but we can still make some conclusions. This is the graph of f, and then h is defined to be the integral 1 to x of f t dt. So h again is an area finder. In part A, they ask you to find h of 1. So following the equation straight up, I'm just going to plug in a 1 everywhere I see an x. In this case, that ends up being kind of nice because h of 1 is the integral from 1 to 1, f of t dt, which is going to be 0. There's no width to this region, so the area has to be 0. Find h prime to 4. Well, first let's find h prime of x. Again, the fundamental theorem tells us that the derivative of an integral is the integrand as a function of x. From there, we'll plug in 4. So h prime to 4, same as f of 4. From the graph, we can look up and see that that is 2. Part C, on what intervals or intervals is the graph of h concave up? Justify your answer. So again, we want to see when does h primed increase. And since h primed is f, I can look up and see that that occurs from 1 to 3 and also from 6 to 7. Finally, in part D, find the value of x at which h has its minimum. It doesn't say local, so this is assumed to be the absolute minimum on the closed interval 1 to 7. Justify your answer. So I need to consider the endpoints, h of 1, h of 7, and I also need to consider any critical points. So critical points are when h primed equals 0, and h primed is the same as f. Looking at the graph of f, we can see that x equals 5 is a critical point, as is x equals 7, but 7 is already a endpoint, so I'm not going to include it twice. And so these are the three values I need to compare. Now h of 1 we've already calculated in part A. That's 0. H of 7 and h of 5 now have to be compared, and I have no way of calculating their exact value. Okay, so I need to be able to come up with some kind of logic, some kind of argument, which one is larger and why. We can clearly see that h of 5 is a positive number because h of 5 represents the area from 1 to 5 underneath this curve. Got to be a positive number. Now, what about h of 7? Well, h of 7 would be the area from 1 up to 7, the signed area, which means we'd be tacking on some negative area onto there. So I can kind of intuitively say that h of 7 is less than h of 5, but I need to have a good calculus argument for that. So let's make a sign chart like we generally would for h prime of x. H prime being the same as f. Okay. So my domain here is restricted to 1 to 7, and we have 5 as our critical number. Prior to 5, h prime, which is f, is positive, and after 5, h prime, which is also f, is negative. Okay, so this tells me that h increases until 5 and then decreases from 5 to 7. Okay? So as a justification, I would say, first of all, h of 1 equals 0. H increases from 1 to 5. And decreases until 7. So h of 5 is a local min, and not only that, it's the only local min. Therefore, it is the absolute, or I should say absolute max, is the only local max, therefore is the absolute max. Now, they didn't ask for the absolute max, they asked for the absolute min, so now we have to compare h of 7 with h of 1. And how would we compare this? Well, We know h of 1 is 0. Do we know the sign of h of 7? H of 7 is also a positive number, and therefore it's more than h of 1. So h of 7 has to be greater than 0. Why? Because the integral from 1 to 7, f of t dt, is positive because more area is found above the x-axis. So these justifications are a little bit different than previous ones because we can't bring in any numerical data, but we can use the area underneath the graph, and we can also use positive, negative, and 0 values to compare function values here. Pause recording. This problem is similar to the last one, but we'll have a couple new nuances here. Once again, we have a function that's given. The graph of f is given here. And h is defined to be the integral from 0 to x over 2 plus 3 of f dt. So h is a area finder again, but it's slightly different because of the limits involved here. The limits are not simply 0 to x, they are 0 to x over 2 plus 3. So that changes things just a little bit here. Alright, so let's find the domain of h. Well, what does h do? H finds the area from 0 up until this point, x over 2 plus 3. Well, f is only defined from 0 to 5. So here's what we know. We know this upper limit, x over 2 plus 3, has to live between 5 and 0. So if you set up a little compound inequality, we can solve for x and be in business here. Okay, so if we subtract 3 from both sides, we'll get negative 3 is less than or equal to x over 2, which is less than or equal to 2. Multiply both sides by 2, we have negative 6 less than or equal to x, which is less than or equal to 4. So this will be the domain for the area finder h. We can double check, plug this negative 6 back into x over here, and we'll get negative 3 plus 3, which is 0, which makes sense. I can find the area starting at 0. And if we plug in a 4, we'll get 4 over 2, which is 2. 2 plus 3 is 5, and that makes sense because I can go up to 5 for the graph of f. Okay, now finding h prime of 2 is slightly different than before. We take the derivative of both sides, and we use the fundamental theorem that says the derivative of an integral function is the integrand as a function of, in this case, x over 2 plus 3. But because this is not plain old x, I now have to use the chain rule and multiply by the derivative of that upper limit, x over 2 plus 3. So this is the fundamental theorem used with the chain rule, which is very useful application in many instances. When you don't have the ability to take antiderivatives, you're going to need to do it this way. The derivative of x over 2 plus 3 is 1/2. So this is our derivative of h, and they're asking for the derivative of h at 2. And so h prime of 2 would be f of 4 times 1/2. F of 4 from the graph is negative 3, so we have negative 3/2. Finally, we're going to look at what x is h of x a minimum, and that's once again assumed to be absolute minimum. So we will test the endpoints, h of negative 6, h of 4, and we'll also test any critical points. So we need to look at the derivative of h, which is up above f of x over 2 plus 3 times 1/2. And critical points are when this is equal to 0. So we'll set this equal to 0 and take a look. F of x over 2 plus 3 times 1/2 equals 0. Multiply both sides by 2 to get rid of the 1/2. We still have a 0 here. And now I need to ask myself, when does this function f of this input equal 0? And I need to look at this graph and say, well, f's graph equals 0 when x is 2. So that means this input needs to be 2. So I'm going to solve this equation here. 2 equals x over 2 plus 3. And solve this for x. That would be my critical value. So we have -1 equals x over 2. And therefore x equals -2 should be the critical number. And we can double check by plugging in the -2 into this input here, and you'll see you'll get f of 2, which is 0. And so those are my 3 candidates to test. And once again, we're not going to be able to get numerical answers necessarily, but we need to be able to compare these values. All right, what is h of -6? H of -6 is going to be the integral from 0 to 0 f of t dt. This one we can calculate. This is 0. H of 4 would be the integral from 0 to 4 f of t dt. And h of -2 will be the integral from 0 to 2 f of t dt. And sorry, there should have been a 5 here, the endpoint. Okay, now we need to compare h of 4 versus h of -2, which means comparing the area from 0 to 2 underneath this graph of f. Okay, well clearly that's a positive number. There is area only above the x-axis in that picture. And h of 4, which is the integral from 0 to 5, would be this signed area. And I should be able to tell this is going to be a negative number because there's more area found below the x-axis than above the x-axis. Okay, so show the analysis that leads to your conclusion. This analysis should be sufficient because I have shown you values for the endpoints and the only critical point in this interval, -6 to 4. Pause recording. Okay, 2 more problems to look at here. This function, f, is defined as an integral, and we're asked to find when this function is concave up. So generally speaking, to answer this question, I usually will find the second derivative and look and see where the second derivative is positive. So that's my general strategy here. So we're going to find the second derivative, make a sign chart, and look where it's positive. Well, to get to the second derivative, I first need the first derivative, and here we use our fundamental theorem again. The derivative of an integral function is the integrand as a function of x. So f prime of x will equal 1 over 1 plus x squared, which I'm going to rewrite as 1 plus x squared to the -1, because my next step is to take the derivative of this to get f double primed. And I'd rather use the power rule here than the quotient rule if I do have to. So power rule says bring the exponent down, change the exponent by subtracting 1, and then multiply, in this case, by the derivative of the inside. This is the chain rule. So we'll multiply this by the derivative of 1 plus x squared. So I'm going to go ahead and move the 1 plus x squared to -2 to the denominator. Leave the -1 with the numerator. And the derivative of 1 plus x squared is going to be 1 plus 2x. This is my second derivative. So I now need to make a sign chart for the second derivative, and look and see when the second derivative is positive. This will tell me when f is concave up. Okay, so I need to know when is the second derivative 0. That occurs when the numerator is 0 and the bottom is not. This is when x is negative 1/2. The other critical points would happen if the denominator was 0. But if I do a quick test of the discriminant b squared minus 4ac, since the bottom is quadratic, I'll see that 1 squared minus 4 times 1 times 1 is less than 0. This means that there are no real solutions to the denominator being equal to 0, so I don't have to look any further. And then a sign test will show that before negative 1/2 will have positive values for second derivative, and after will have negative values. And so therefore my interval for f being concave up will be negative infinity until negative 1/2. And let's look at one more here. This interesting equation asks you to find a function f, so we want the formula for f, and then find the real number a so that this is true. And to get f out of this integral, I need to somehow wipe out the integral, and we'll do that by taking the derivative of both sides. So we have the derivative of 6 plus the derivative of this integral. Is equal to the derivative of 2 times the square root of x, which I'm going to go ahead and rewrite as 2x to the half. Okay, the derivative of 6 is 0. The fundamental theorem has told us that the derivative of an integral function is the integrand as a function of x. So this becomes f of x over x squared. The derivative of 2x to the 1/2 is going to be 1/2 times 2, which is 1, times x to the negative 1/2. And as long as x is not equal to 0, I may multiply both sides of this equation by x squared. So f of x will equal x squared times x to the negative 1/2, which will simplify to x to the 3/2. So there's our f. That's the first part of what they asked us to do. They now want us to find the number a that makes this equation true. So now we have 6 plus the integral from a to x, f of t, which would be t to the 3/2, over t squared, is equal to 2 times the square root of x. We'll now use the other part of the fundamental theorem, which says, how do I do a definite integral? First, we'll simplify the integrand. This will become t to the negative 1/2. I forgot the dt up here. Is equal to, same thing, 2 times the square root of x. Now, we need an antiderivative for t to the negative 1/2, which is 2 t to the half, or square root t. We'll plug in our limits and subtract, and we're still equal to 2 times the square root of x. 6 plus 2 times the square root of x minus 2 times the square root of a is equal to 2 times the square root of x. On both sides we have a 2 times the square root of x. They may cancel. We can move the negative 2 square root of a to the other side by adding the same thing to both sides. And solving for a, we're going to get 3 is equal to the square root of a, so a is 9.